Welcome to Calculus. Today we will investigate differentiating polynomial functions, focusing on creating rules based on the definition of the derivative. We'll begin with very simple functions and build to larger polynomials by creating additional rules. Our first example out of 5 total is a constant function. So we've got here y equals 4 pi. So over on our chart, we need to identify which of those pertains to a constant function. So that's this first one. So what we want to do is we want to come up with a rule that we can create here based on the definition of the derivative. So we're looking at that first entry, the first row there. So we're going to say that in general, if f of x equals a, so let's take a look at what that would look like in the definition. So remember, the definition of a derivative is the limit as h approaches 0 of f of x plus h minus just plain f of x, all divided by h. If we're taking our constant function to be this f of x equals a, the way we would substitute into these two expressions, f of x plus h and f of x, would be simply a and a. Because in the case of a constant function, there is no x to compose in x plus h or just simply x. When we reduce that down, we see that that numerator is going to equal 0. So that equals the limit as h approaches 0 of 0 divided by h, but 0 divided by anything is 0. So that's the limit as h approaches 0 of 0. And at that point, my h is gone. So the whole limit equals 0. And that's our first rule here, the derivative of a constant function. So I'm going to fill in here, if f of x equals a, where a is a constant, then the derivative of f of x, using that prime notation, is d over dx, ddx of the function a, that's the Leibniz notation, equals 0. Now, once we've built that rule, to apply it, we just find our constant function. So here we're looking at y equals 4 pi. And immediately, by applying this rule, I can see that the derivative of y, or in Leibniz notation, ddx of 4 pi, immediately equals 0. And that's the beauty of the rule. Once we establish it based on the definition of the derivative, we can use the rule and apply it very quickly to come up with derivatives of, in this case, a constant function. Keep in mind that what we're describing there is that the slope of all tangent lines of a horizontal line will be 0. That slope is 0. Well, let's keep building. So there we saw the derivative of a constant function. And here we've got a linear function. So now we're looking at g of x equals 4x. So really we need two additional rules. So the ones that we're going to need are this derivative of f of x equals x. That's the linear parent function. And we'll also need something for the constant multiple rule. So again, the derivative of f of x equals x is about this x part. The derivative of the constant multiple is about that coefficient of 4. So we just need to come up with two rules, and then we can apply them to find the derivative of g of x. Well, again, let's go to our definition of the derivative. So for the linear parent, we're going to do the limit as h approaches 0 of f of x plus h minus f of x. So same definition we've been looking at, all over h. So what we'll do is we're going to compose into the function f of x equals x this sum x plus h. Well, that's going to be x plus h. And f of x we already know is simply x, and that is our next step. So what we see in our numerator is an immediate cancellation. If I let the parentheses go, we've got x minus h minus x. So what we see will cancel are my two x terms. And I'm sorry, that's x plus h. And what that gives us is now the limit as h approaches 0 of h in my numerator divided by that h in the denominator. And that's a quotient of 1. So it's the limit as h approaches 0 of 1. And again, I don't have any occurrences of h left, so the limit simply equals 1. And there's a rule for us for the derivative of the linear parent function f of x equals x. If f of x equals x, then the derivative of f of x, or in Leibniz notation, d dx of x equals 1. So we'll apply that here. We also need to see about constant multiple rule before we can take the derivative of g of x. So for the constant multiple rule, we're going to say that we have a large function f of x equals k times f of x. So we'll set up our definition of the derivative. So the limit as h approaches 0 of, we'll use the large function f x plus h minus f at x all over h. So if we're assuming that f of x is a constant times a small function, what we'll do first is substitute in k times f of x small plus h minus, and again the large function is defined here as k times f of x. And at that point, what I'm noticing is that I have two occurrences of the constant that I can factor out. And by the properties of limits, I can factor it out to the far left side. So the way this turns out is this equals k factored out times the limit of f of x plus h minus f of x. That's what's left after I factor out the k over h. And this whole limit, let me put as h approaches 0, is in fact the derivative of f of x. So the bottom line here is that if I've got the limit of a function that's a constant times another function, it is that constant times the derivative of the function. And that we can write. Large f prime x equals k times the derivative of small f of x. So two rules that we want to apply here: the derivative of the linear function f of x equals x and the constant multiple rule. Turns out that the derivative of g of x is going to be the constant 4 times the derivative of x, which is 1. And that gives us our final answer. The derivative of g of x equals 4. So at this point, we've seen 3 of our rules defined using the definition of the derivative. Let's add to those another rule, the simple power rule. In fact, we'll add 2 more, the simple power rule and the sum rule. So I'm going to erase here so we have a chance to fill in. So our new function here is y equals 5x squared plus 4x. So notice part of this we can do already. The 4x is in fact that same function that we just took the derivative of. But we need something that we can use when I've got x to some power, basically a simple power expression. So that rule is here as the simple power rule. So I want to fill in there. Let me indicate here. And instead of going through the binomial expansion of that definition of the derivative, let's just give that one as a rule directly. So if I've got some y equals x to the power of n, where that power is greater than 1 and an integer. So no fractions, just natural numbers. Then the derivative of y, which is in Leibniz notation d dx of x to the power of n, two things occur. The old power comes down as a coefficient, so that equals n times x to the power of 1 less than the original power. So x to the power of n minus 1. And that is a powerful simple power rule. Now we are going to need one more rule here in order to complete this derivative, which is the sum rule. And again, that's because I have addition there. So the way that we're showing this is that if I've got two functions, f of x and g of x, that are differentiable so that I got a bigger function is the sum of the two of them. And you can guess how this one goes. The derivative of the large function equals the derivative of the individual functions added together. So f prime of x equals f prime of x plus g prime of x. So again, we got two new rules. And in addition to our other rules, we can now take derivative of this function y. So let's write y prime equals d dx. So again, this is just equivalent. I'm just showing one's prime notation, one's Leibniz, of the function 5x squared plus 4x. So let's take care of that first term, 5x squared. So by the constant multiple rule, I'm going to place the 5 out front. And then by the simple power rule, I'm going to bring the old power out as a coefficient, base x to the power of 2 less 1. We'll simplify that in a moment. Now for that 4x. So again, we'll apply the sum rule. So we're just working by pieces. Each term is its own separate derivative. And 4x has a constant, so applying the constant multiple rule, the 4 sets out front. And then the derivative of f of x equals x is 1. And that's ready to simplify entirely. So all I have to do is reduce everything down. So this is 5 times 2 is 10. X to the power of 2 minus 1 is 1. So I could write it or I could omit it. Plus 4 times 1 is 4. And that completes the derivative of this y function, which originally was 5x squared plus 4x. Let's take a look at one of these where we apply the last rule, the difference rule. So here I've got basically my entire table populated with the rules, and I've got something that's a little more complicated. So again, this is a sum, so we'll just hold off on our last rule, the difference rule. We can calculate the derivative of f of x with the 5 rules we have completed. So again, just to take it part by part, the derivative of f of x, which if I look at the original f of x here, it's got 2 terms with a sum. So I'm going to start just by observing the sum rule. I'll differentiate by term. For that first term, 3x to the power of 5, I need to start off with the constant multiple rule, which says leave the constant multiple out front, unchanged. And then I also need to apply the simple power rule to deal with the derivative of x to the 5th. So remember, I take the old power down as a coefficient, 5, base x to the power of 1 less than the original power, so 5 minus 1. And that takes care of that first term. So then I am going to apply the sum rule. And here I have an instance where I need to use the constant multiple rule for an irrational constant. So square root of 2 is shown up on the right-hand side, and that's just a notational habit there so that I know that only 2 is under the radical, but it is a constant. So the only thing I have to note here is the order. I'm going to leave the constant in the term unchanged. And then I'm going to treat that x to the power of 3 using the simple power rule. So 3 comes down as a coefficient times base x to the power of 1 less than the original power of 3. And that, again, is ready to simplify now. So this equals 3 times 5, 15. X to the power of 5 minus 1 is 4. Plus 3. Now I'm going to leave the 3 separated from the other constant multiple, square root of 2, just again as a consideration of keeping just the 2 under the radical. And that completes the derivative of this function f of x. All right, so our last example, you guessed it, is about the difference rule. So here I've got 3 terms, but again, nothing is new in terms of new rules except for this difference rule, because I have both a subtraction and an addition. Well, let's fill in for that last rule. And I'm going to pick up and write there, really similar to our sum rule. So let's read the hypothesis part of the statement. If f of x and g of x are differentiable so that large f of x equals small f of x minus g of x, then the derivative of large f of x equals the derivatives of small f of x minus separately the derivative of g of x. So very similar to the sum rule there. And easy to apply. So as I look at this derivative of y, I'm going to say that the derivative of y equals, so just again, looking at my parts here, I've got a constant multiple, so square root of 2. Again, I'll leave it on the right side. And then I've also got a simple power. Bring down the old power as a coefficient times the base x to the power of 3 minus 1, so 1 less than the original power. And then minus, applying the difference rule. And then again, I got a power here, or I'm sorry, a constant multiple 5 halves. That can stay on the left, as is tradition, times the simple power x squared. So that's going to be times old power becomes the new coefficient, 2x to the power of old power minus 1. And then apply the sum rule. And again, I've got a constant multiple square root of 2. And then lastly, I have the derivative of the linear parent x, which is simply 1. And all we've got to do now is simplify and reduce. So y prime, or the derivative of y, is 3x squared square root of 2 minus, I have 2's canceling, 5x to the power of 1, or I can just omit the 1, plus 1 times square root of 2, which is simply the square root of 2. And that completes the derivative of the function y. Thank you for joining for this investigation of derivative rules for polynomials. I'll let you go differentiate your own polynomials. See you soon.